Hi, my name is Alex Cabrera. I'm a PhD student at Carnegie Mellon University. Today, I'll be talking about our work on auditing AI models with crowdsourced failure reports. AI systems are deployed in many real-world domains, which means that when they fail, they can have significant real-world consequences. This includes everything ranging from fairness issues, for example, biased hiring algorithms, to safety issues like self-driving car accidents. Knowing what systematic errors the AI systems are making is essential, both to help developers improve their models and to make decisions about whether they should be using them at all. In a review of some existing empirical work, we found that there are two main challenges preventing developers from knowing how their models are failing. First is just discovering what the initial errors are. This might be because the examples aren't in the test set, so they can't actually discover how they're failing. Or even if they are present in a test set, there might be hundreds of thousands of instances, and it's hard to parse through all the errors to find any patterns of failure. Once developers have a hypothesis of how their model is failing, it can often be hard to validate those failures. Does it generalize, for example? Is it just a one-off error, or is this a more systematic failure that the model has? And also, is this description of the failure accurate, or is it confounded? In this case, for example, maybe I think the model fails for people with clear glasses, but maybe it just happens to be that all the people with clear glasses are looking sideways, the real cause of the failure. To try to tackle this challenge and help developers debug their AI systems, we took inspiration from bug reporting in software engineering. In software systems, when users run into issues, they can write a bug report with a description of what happened, maybe some additional context like a stack trace, and some steps to reproduce the issue. The developer can go and use that information to debug their system. So we thought, why not take a similar approach to AI systems? Why don't we ask end users why the model failed? Unfortunately, it's not so easy. We don't have as much context as we do for software. We don't have stack traces. We don't have steps to reproduce. We really just have the instance that failed and what the user thinks the problem is, why the model potentially failed for that instance. So we term these descriptions failure reports, descriptions of how or why the user thinks that the model failed for a certain instance. And the example we see here is eyeglass detection. This was inspired by me going through immigration once, and they had a kiosk that asked me to take off my glasses. They had a model that could detect whether someone was wearing glasses to take a picture. So this is the example model we'll use throughout this talk. So we can collect a bunch of these reports, but we kind of go back to these original two challenges. First, it's either we have a bunch of these textual reports and we have to sift through them to actually find any patterns of error. What are the common frequent model failures that people are reporting? And even if we're able to go through and discover all these patterns, how do we actually validate and verify that those generalize? They're not one-off errors, or they're not confounded by other reasons why the model might be failing. So to tackle this challenge, now that we have these failure reports and we want to make sense of them, we developed a visual analytics system that we call Deblinder. Deblinder has two major areas. The first is the failure report embedding, and this primarily tackles challenge one. How do we help users make sense of these failure reports and find these general patterns of failure that end users are reporting? And next, we have the hypothesis panel. The hypothesis panel tackles challenge two. How do we help people verify the patterns that they're finding and the generalized patterns that people are reporting? So first, we'll look at the failure report embedding and how we designed it to help developers actually explore these failure reports. So what we do is we take all the failure reports and we extract the key phrases from them. And then we weigh them by how frequent they are, and we lay them out semantically together. So here, for example, we can see a lot of the reports for glasses, frames are all together, maybe wearing. So those are all the ones that maybe have to do with glasses. Here we can see that the user has highlighted thin frames. There seem to be a lot of reports saying that thin frames are a potential reason for why the model is failing. And when you hover, you can see example images and the actual text descriptions that users gave. So once the developer has gone through and found some of these patterns of failure, they can actually go on and start tracking and validating their hypotheses. So they can first go in and select all the different instances that match a hypothesis. In this example, they have a hypothesis that the model's failing for people with thin-rimmed glasses. So they can add these to their hypotheses. And now we have what we call a couple validation methods. So now, okay, maybe I think that my model's failing for people with thin glasses. How do I actually validate that that's true? How do I tackle that second major challenge? So we have two methods for this. One is image search. So you can just straight up look for additional images or instances that fit this description, or image manipulation, counterfactuals. So you can actually directly manipulate the image and see how the model changes to directly test your hypothesis. So we'll just show an example of the similar image search. For thin-rimmed glasses, we actually have a mechanism. You can go look in Flickr or automatically in Google, upload these new images, see the model outputs, and actually decide whether or not the model was right or wrong for them, and see if that percentage matches. Is it that 50% of the time people with clear glasses are misclassified, or is it pretty accurate and matches the overall accuracy of the model? You can do a similar thing with counterfactuals, edit the image, re-upload it, and see how the model prediction changes. So to test whether developers can actually use Deblinder to find these systematic errors, we ran a user study with 10 PhD candidates and ML practitioners. We had collected a bunch of reports using Amazon Mechanical Turk for this eyeglass detection problem, and then had them go through and develop these different hypotheses. We found that there was a lot of consistency in the types of hypotheses that developers came up with, and that this sense-making process of finding, creating hypotheses, and verifying them made a lot of sense. But the last thing we wanted to test is we're kind of just asking people what they think the model failed on. What semantic aspect of the image caused the model to fail. And we don't really know if that correlates directly to what the model is failing on. So to test this, we decided to directly gather data from the hypotheses the developers had come up with. So we had first just the baseline data set. So this was about 60,000 images from the Celeb training data. And then we decided to augment it with, say, an additional 600 images just from Google Images, just headshots of people with and without glasses. Nothing interesting. In our last condition, we decided to do the baseline plus these blind spot images, these systematic errors that the developers in our user study had found often. So people looking sideways, people with clear glasses, all these different descriptions that the developers had extracted from the reports that end users, crowd workers on Amazon Mechanical Turk, had come up with. And when you actually plot this over time, this yellow curve is this augmented data set with the images specifically from these systematic failures. And the X is the baseline, the blue, number of instances. And as we increase the baseline number of instances at every training set until we get to the end, and it kind of asymptotically joins, including these specific blind spot images leads to significantly better F1 score than the other two conditions. This is a very good heuristic and indicator that collecting data from these systematic failures can improve model performance and is identifying these areas where the models might not have enough data, or that these types of instances might be unrepresented. So overall, this process we kind of define as this crowd auditing process. We take crowd input. A developer goes through the sense-making process to kind of parse that data, test these hypotheses, and they can take that information, update their models, either gathering more data or updating their model architectures, and redeploy that into the wild. And this iterative process can be ongoing. So lastly, there's just some open questions. We kind of empirically validated that the insights that end users have do correlate to model failures, but some formal testing of whether human insights of why a model might fail correlate with the actual reasons a model might fail could be very interesting, including more direct ways of improving models, and finding more efficient methods for validating hypotheses, maybe in some automated ways. In sum, we introduced the idea of crowdsourced failure reports and develop a visual analytics system, Deblinder, that helps end users actually use them to discover systematic failures in AI systems. Thank you very much.